Okay, so the complex case. In this case, I didn't actually compute the exact solution for all of these systems because we can describe the behavior quickly just looking at the eigenvalues and vector, the eigenvalues. That's it, just the eigenvalues. So it will be actually similar to what you have seen in the case of a single ODE, the homogeneous second order ODE, when you have complex characteristic roots. So once again, remember that in the complex case, your solution looks like this, right? So it's a linear combination of those two terms that contain an exponential and some combination of sine and cosine. In the complex case, whether the solution approaches zero or not, it's completely determined by the real part. Remember, the sine and cosine don't converge to zero, right? I mean, like they, as t goes to infinity, they have a periodic motion, right? So they have some finite amplitude depending on the values of these vectors and the constant, but the divergence or convergence to zero is dictated in the end by the sign of the real part. So that's why you have essentially three major cases because of the sign of alpha, of the real part, which could be either positive, negative, or zero. Furthermore, you don't have straight line solutions anymore. The motion is always, motion always contains some periodic motion because of this sine or cosine of beta t. And when you actually plot x against y, you have essentially a spiraling motion or rotation around the origin. You're going to have a spiral if you have positive or negative alpha because as you move around the origin because of the sine and cosine, alpha either pulls away the solution from zero or approaches zero, depending on the sign of alpha. So this is an example when alpha is positive. So for this matrix here, if you compute alpha, lambda, you're going to get 2 plus minus I. And that means the real part, alpha is equal to 2, which is positive. So in this case, you're going to have what we call a repelling spiral, which is, of course, unstable. It's another case of unstable equilibrium point. The solution moves away from 0, 0, but it does so not like a node, like the repelling node, but in a spiraling motion. So no matter where you start, the solution moves away from 0, like that. By the way, you can prove, we're not going to go over that in this class, but you can prove that the rotation is either clockwise or counterclockwise, depending again on what you actually throw in here in the equation. You could actually check, especially if you if you took calculus 3, but even if you didn't, I mean, the easiest way to actually check whether the motion is clockwise or counterclockwise, if you don't have the plotter, is to just pick a point, for example, on the horizontal axis, and then compute the tangent vector, and then ask yourself, whether it's pointing upward or downward. So I mean, you pick a line so that if the rotation is one way or another, then you would know immediately one of the components of the tangent vector, whether it's positive or negative. So so yeah, that's one way, but I'm not going to go over into that. So again, it will be either clockwise or counterclockwise, but away from 0. And the opposite case of this, the negative real part. Let's actually write it down on the let's write it down here. So the second case, negative real part, alpha less than 0. Same little trick as before. If you interchange the sign of the main diagonal, you get the same eigenvalue, but with the negative real part, with the opposite in sign real part. So if it was 2 for this example, by interchanging the signs on the main diagonal, you're going to get minus 2 plus minus I. So lambda is minus 2 plus minus I, alpha equals minus 2, which is obviously negative. And the picture will be very similar. The solution moves towards 0 if you start at any point in a spiraling motion, right? Like that. So this will be what we're going to call an attracting spiral. And of course 0, 0 will be a stable point. Attracting spiral. Oh, another thing I'm going to show you actually with the computer. Sometimes you don't see too many spirals because the convergence to 0 is very fast. In fact, with this alpha, it's going to be so fast, you're not going to see too many rotations all the way around the point until it reaches the equilibrium. If you want to see many rotations before the convergence, I mean before it gets close to the 0, 0, one other trick of the trade is you make, you scale down the main diagonal, and that causes a scaling down on the alpha. So you make alpha smaller, and that will cause the convergence to be smaller. I'll show you with the Camtasia. So finally, the last case, 0 real part. And you should probably anticipate what happens here from the analogy with the single ODE. If you have a 0 real part, there is no exponential in the solution. So that means you have a fully periodic motion. So the solution is fully periodic. There is no convergence to 0 or divergence from it. So that's another case of neutrally stable point. Another name for it is a center, because when you plot x against y, they form a complete loop. So here's a typical example, minus 1, 1, and minus 5, 1. And if you compute lambda, you will see this is going to be plus minus 2i. So that means alpha is equal to 0. And if you sketch the solution, if you run the system with the plotter, anywhere you click, you're going to get a complete loop, closed loop like that. And the solution is periodic. Yeah, so I mean x and y move on a complete loop, which means that if you plot, of course, with respect to the time t, each x and y, they will be fully periodic, right? They won't attain, of course, the high and the low at the same time point. That's why you have a complete loop. But independently, with respect to the time t, you will have a periodic motion. That's not really nice picture because it looks like it converges to 0, but it's a fully periodic motion. You will see with the plotter in the xy plane and the phase plane, that's equivalent to a complete loop. So that's the full classification of 2x2 linear systems and the geometry. Just to anticipate the last part, I mean, there will be basically 2 more lectures after this one. We're going to deal with the non-homogeneous case, how to solve the non-homogeneous systems, and we will revisit these concepts at the end when we analyze non-linear systems via linearization, via linear systems basically. And to anticipate a little bit, that method of linearization will only be applicable if the associated linear system has non-zero eigenvalues. So these cases of 0 real part, or in the real case, 0 eigenvalues, those will be exception cases that are not applicable for the last topic of the class, namely the linearization of nonlinear systems. But we'll get to that when the time comes in the last lecture. So that's it for today.